All right. Hi, guys. So, in this, we are going to be learning assembly features, and we're going to be learning full sketch or full robot sketches. We're also going to be going over briefly if you have to use gears, um, and we're going to be trying to implement some smart design in there as well. So let me just hide my settings here. All right, here we go. So we'll go ahead and we'll start with these big robot sketches. So if you don't know quite what I'm talking about, if I wanted to sort of design my robot or get a good idea of what it's going to look like, I would want to do it on my sketch plane. And so we can start by we'll take this from a side view. So we're viewing like the wheels side right now. So my wheels, I'll just briefly put in. There's my chassis. There's one wheel. There's two wheels. There's three wheels, and then we'll dimension these out. Set that to inches. Gotta edit sketch. All right, and then we'll make that. We'll say it's 4 inches because we can't use, okay, we can't use 6-inch Coulsons anymore. So 4 inches and 4 inches. There we go. And so we'll space these out. Like that. And we'll make our whole chassis thing bigger. Yep, like that. And this is where I decide how long do I want my robot. We're gonna go with a pretty normal, like 24 inches. I don't know. That's a little long. We can go with 20 inches. So we'll just set the wheels sort of within there. I want this one to be in the middle. And then I want this wheel to be over here. And then the way I'd sort of dimension these out is these are going to be vertical. And then I'm going to make a center line that goes from here to there. And I want to make sure that this is not horizontal, but that these are horizontal. And then the height distance between these two, if I pull away, yep, if you pull at a certain place, like real far away in this direction, you can get the height um, of the diagonal. So we want a drop center, which is going to be about, it could be between an eighth or a 16th. We're going to go with the 16th. There's not a lot of obstacles in this theoretical game. And then we're going to set these lines here equal to each other. So now the distance is equidistant. The only thing that we have not constrained so far is this distance and this distance. So we'll go ahead and we'll mark from the edge that we want this to be about a little bit more than 2 inches away. So we'll say 2.125. It gives me about an eighth. Actually, we'll go with 2.25. That is the 2-inch radius plus a little bit more. Our thickness of sheet metal, assuming that this is sheet metal, is 1/16 of an inch, and That will give us about 3/16 of space between the wheel and the edge of the chassis, and it gives us a little bit of wiggle room in case we want to make something a little thicker right there. So this looks pretty good right now. Now all we need to do is constrain how big we want this. And for this, we need to do a little bit more circles. So I need to put a circle right here. And I need to, well, first I need to figure out how tall my overall base is. And we're going to say, by the way, it's very handy for you to have a ruler at your workspace because then you can kind of visualize things a little better. We're going to say that this is going to be 4 inches tall. We're going to say it's 4 inches tall? No, these are 4-inch wheels. Let's see how 3 inches looks. 3 inches looks pretty good. Yeah, I'd say that looks pretty nice. And we can go back and we can change that. But yeah, overall, that looks pretty good. It clears the wheels. It's all good. Okay, so this circle right here, this is gonna be a bearing size. So this is gonna be 1.125 because we're gonna be using a 1/2 inch hex through this. And then that distance right there between the bearing and the edge of the frame, I'm gonna say I want it to be, here we can use equations, 1.125 divided by 2 plus, and then I want the distance between the bottom of the bearing and the top of the floor of the robot, and I want that to be about, we'll be generous, we'll say 3/8, we'll say 1/4, so 0.25. And yeah, that looks pretty good. All right, so now you can see everything is defined. That's really nice. So now that we've sort of got a good idea of what our overall chassis is going to look like, now we can sort of play around with the actual distances. I know we sort of set this right here at a certain height. Well, this won't change, but the distance right here, I know we set that to be 2.25, but in reality, what this is going to be based on is the chain distance, and the chain distance is right here. And there's a whole lot of things that we can go into with chain calculations and figuring out the right distance for your sprockets, or if you're using belts, it's the same thing. Whatever distance your belts are from one another. I think we'll actually use timing belts for this. So let's go to products to belt calculator. I'll send a link out, I believe. It's already out in one of the papers that I sent out. Oh, and is SolidWorks done? Yep. All right, so this is about 7.75 inches. So my desired center is 7.75. We use HDD, and we use 5mm for our drivetrain. But we're gonna go ahead and we're gonna use, I don't even remember which ones are common. Let me just look up Next Pro timing belt. 18, 24, 30, and 36. How big is an 18? An 18 outer diameter is 1.126. So looking at my, that's about a, that's a little small. It really shouldn't matter. I think we'll go ahead with 18. But we'll play around with 24 in case it doesn't give us quite a wonderful, yeah, it does not give us a great distance here. It's either between 7 inches, which is a whole 75, 3/4 of an inch difference, and this is about 1/4 of an inch difference. So let's see if it's better with a 24 to 24. All right, that's pretty good. Is 104 a common belt size? So we'll go back and we'll go to belts and pulleys. HT, oh, that's 15 millimeter width. That's not what I want. 9. What? 5. What? Huh? I think I'm confusing myself. I think this is what we use. Yeah, okay, 104. Out of stock for the 2020 season. Doesn't matter. We're using this. So 104 is a common size. I don't know why it is, but it is. And 7.874 is our distance that we want. So we'll go over here and we'll go ahead and we will delete this dimension. And then we'll go ahead right here, 7.874. Enter. Now you'll notice that that should make things blue. But it didn't make things blue. Why? Because I can still change this distance. It doesn't matter what I plug in to this right here, because ultimately the only thing that matters is smart dimension. And so if I can get the right dimension, I don't know if this is at an angle or not, which is the annoying thing about all these dimension things. So here, this is what we do. We go the distance between those two. It does seem to be going at an angle. Is that at an angle? No, it's straight. Crap, that's annoying. So if you can't tell what I'm trying to do, I'm trying to get, so how this right here, we pulled it across and we were able to find the height. What it's trying to find is the distance on this plane right here. Whereas I want the overall distance of the diagonal here. So what we'll go ahead and do is we'll be a little cheeky. We'll call this 1 inch. And then we'll call this right there. I'm sure Ryan is screaming at me like, do the freaking thing, Dan. Sorry, Ryan, I don't know how to do the freaking thing. I'm sure there's a much better way to do this. But then we go over here, then we go back, not to that one, to this one. And then we go 0.06, oh, 0625. And then it should still be 7.874. There we go. And that's what, double check, that's what we want. 874, yes it is. All right, so that was a really annoying way of having to do that, but I don't really know any better way to do that. I'm sure Ryan does, but heck if I know. All right, so now that we've gotten this, What we're gonna do is that we can kind of use that for our drive base then. We don't want to plan out everything because this is just going to be like a rough design, but this will give us pretty much everything we need. We have our height clearance, we have the overall height of our robot, we have the length of our robot. Um, that distance should be good. Um, we know what size wheels we're using, we know what size drop center we're using. Um, now we just need to figure out some of the mechanisms. So we'll go ahead and we'll say that we're going to have an elevator on here. So we'll go ahead and we'll make an elevator. Corner rectangle. I'm going to make it not flush with that just in case I want to change it. And if you don't know, for our elevators, we use VersaFrame, so that's 2 inches. And then this, we're going to say, if the height limit's usually like 48, we're going to say that's 20. Oh my golly. Cancel. And so ideally this would be somewhere in the middle of our robot. And then we will have this on a transmission. And so we can roughly say that our transmission is like, we don't really care about the transmission right now. We'll say that our gearbox, our drivetrain gearbox, we're going to say that's about right there. For our elevator gearbox, we're going to say it's about right there. And then that will give us a little bit of space under here. We can move this up and down for a few electronics maybe. But primarily this right here is going to be where our battery is and some of our heavier electronics are to sort of balance this weight out. All right, and then let's see. Yeah, here is, we'll go ahead and say that this is actually flush with this for convenience. Then we'll go ahead and we'll say that that's 8 inches. No, 9 inches. We'll say it's right in the middle. And then these are sort of general things for our gearboxes, so I'll just put them for construction. We don't really care about them right now. All right, and so let's say I'm gonna want I'm gonna want something like a outside the bumper intake that's gonna pop out, but it's not gonna go up and down with my elevator. It's gonna be separate from my elevator. So I'll have, this is gonna be my elevator, and then this is gonna be whatever the carriage is on my elevator, yada yada yada. I also have another thing, another elevator thing, stage. That's what it's called. We'll go like that. It's 2 inches as well. So instead of smart dimensioning that, we can say that it is equal. And we can say that these two things are collinear. That way I can slide this up and down. I can slide this up and down. And then we'll go ahead and we'll say that it's not quite 20, but instead it's going to be 18 inches. That's a pretty safe bet. And then it'll go up to about right there. And then this is our arm, and it will go up to about right there. And that's really good at math. Sorry, guys. Should be like 3 inches. We'll say that's like another 1.5 inches right there. And then 20 inches plus like 17, 16 inches, that's 26. 26 plus 4.5, that's like 30.5. So assuming our, okay, we'll just say for the sake of the game that this is perfectly fine. I don't actually know whatever the heck the height limit is for our imaginary game, but we'll just say that this works fine. If we did have a height limit, we change this to be up to the height limit of our starting configuration, and then we'll change this stuff, and then we might add like another stage here on the arm to make it pivot up and down to make it reach the highest configuration that we would need on the robot. So that right there is sort of loosely designing a robot in a sketch. We didn't really put in the thing that comes up and down, but it would actually be a really good chance to talk about linkages. So we'll say, since it'll be hard to sort of space all these out, we'll say that the intake is over here. So I'm going to arbitrarily choose a pivot point right there, and then something that comes out, and then it goes out like that. So I want it to be right there, and then this point, I'll have to fully define this as, I'll say 1/2 inch, 1/2 inch. Actually, no, I should be smarter with that. It should be 0.875, because that's the bearing size for a 3/8 hex. So go ahead and do 0.875 divided by 2 plus 0.125. What was that? 0.5625. And we'll do the same here. 0.5625. So I know last time Nick asked if we had to do relations for everything. No, we don't have to do relationships for everything. Like, I'm using a pretty decent amount of dimensions here. I don't know why I set all of these to be 4 inches. I should have set all of these to be equal. I mean, it's just little things like that that we could do. But I think really it's okay if you use a ton of dimensions. I don't think it's really gonna play a big role. I prefer if we use a lot of dimensions, because then it just makes it much easier in the future if we ever have to change something, but really it shouldn't be a big deal. All right, so right here, you can see I set my distances here, and that's because if I want to move this, I can now do it like that. And so it's a little bit funky because I was moving the whole thing. I was moving the whole arm, not the point itself. So we'll say that this is our roller right here, and we'll say that this is our fully out configuration. Then whenever we're tucked in, we'll say that we're like, we'll want this to be shorter then, or we'll want this to be longer. We'll say that that's 6 inches. We'll say that that's like 5.5. So then it goes out. We'll say that our game piece is like, all right, here's where we get a little bit annoying. So there's our floor. No, I don't want to make a line. This is, okay, it's already tangent. It's already fully defined, wonderful. And for infinite length for construction. Here we go, there's our floor. And then we'll set another ball here, and it's about that size. We'll say that this is like, yeah, 5 inches is good. So we have this ball here. We need our intake to be about right there. And then we also want it, the way linkages work in this particular setup, this point here is going to be running in a straight line. So we can set up a line that goes from here all the way over here, and it is horizontal. Crap. And we can set this point here on this line coincident. And then it will run across, and then we just set the distance right here. We'll say that's about 0.5 inches or something. And then we'll say that this is vertical to this. Can't do that. It has to be this is vertical to this. The 2 points are. And then we'll say that our maximum distance is, oh, it says 9. I think in Power Up it was 12, but we'll go ahead and we'll say that it's only 8. Okay, we'll say it's only 6. Perfect. Yep, that's wonderful. But oh no, wait. Something we didn't account for. We didn't account for bumpers. I don't want to do that right now, so I'm not going to. But that's something you would do. You'd put in your bumpers so then you have a good idea of how your intake would work. There's a lot more we can do with the intake, but this was a little bit too long of a thing on full robot sketches. You can see the idea. We just pick up the thing and then we just go up. This kind of design you're going to see a lot of in early build season, and tonight, whenever we see the game, if we decide to go into robot strategy or robot design after the strategy meeting, then you'll see us pull out these kinds of things. So I'm just going to save in the F4 folder, and I'm going to call this a drawing or something. All right, and the other thing we wanted to go over was an assembly feature. So let me pull up an assembly. Use the bearing block assembly we used last time. That's an assembly. What do you mean? You don't know where that is? Oh, that's right. Because we changed the names whenever we do the thing, we have to change where it was. So change training part actually became the bearing block. Okay. The hex became the bearing block axle. So, oh, excuse me. Whenever you make those names, try to do them right the first time. Otherwise, you'll have to go back and fix everything that you renamed. All right, so assembly features. You can see it's right here. We have whole series, whole wizard, simple hole, extruded cut, revolved cut, swept cut, fillet, chamfer, weld bead, and belt/chain. That's gonna be useful in the future whenever we do the full things. But then there's some other things to look over, like in reference geometry, you can make your own planes, and that's useful if you're doing something like mirror components. And so there's like how there's linear sketch pattern in sketches. This is a linear component pattern, and then you have all these different kinds of things, pattern driven, curve driven, chain component, and then there's mirror components. What you're going to be using the most is probably mirror components and linear components, maybe circular components, but mostly mirror. And so we'll go over how to do that here, and that's right, we fully defined that, and we set that distance. So I think what we'll do first is we'll do a whole series. But to do that, we need to make a new part. So, yep, we'll make a new part. And we'll say that this is our normal 2 inches, just like our other part. So it's 2 inches. I'm in inches. And I'm editing the sketch. Excuse me. And that's 2 inches. All right, so it's 2 inches by 2 inches. And then we'll just add some extra holes. I just want a hole there, a hole there, and a hole there. And so we'll just set these to be vertical, so they slide along that. And I want this distance to be, yeah, ½ inch is good. Let's do 0.625. There we go, that's good. And all these holes are the same. So we'll set those to equal. And we'll set these to be equal. And then we'll go ahead and we'll dimension this out, and we'll make that 0.203. That's the size for a blue. And then we'll go ahead, and I'd like this to be horizontal with this. So once again, we'll make this 0.625. So you might have noticed that I did 4 holes, and for this I'm doing 3 holes, but I'm not doing 1 hole or 2 holes, and that's because if you have a connection, you should try to make it at the very least, 2 bolts. And it would be on like the 2 corners or something. Ideally, you use 3. You don't really need to use 4 because that's a little bit much. But you want at least 3 points of contact. You want at least 3 connections. So we'll just go ahead and we'll extrude this. And we'll say this is, oh man, I'm kind of sleepy. I don't know why, it's 1 in the afternoon. So we'll go ahead and extrude that. Fillet. We want to make sure all these edges are filleted. And a little trick you can do, whenever you select one, if you go up, we can hit this button and it will select all around. So I'll go ahead and cancel that again, just to show you again. I'll click the edge, and then I'll go up here. I'll select that one button, and I don't know why the fill has changed on me, but I'm going to just make it 0.1. All right, that looks pretty good to me. I believe the sketch is fully defined. Yep, we're all good. All right, and so we'll go back over to, we'll have to save this as MX 1.0 114, and we'll say this is we'll say that this is a whole plate. And now we'll go over back to our bang block and we'll insert our whole plate. And I want one on either side. All right, and so luckily those holes are going to line up. And let's just go ahead and make this to the sides. So we'll make that coincident. We'll make this edge coincident. And that should do it for that. Let's just make sure that this face here is coincident with this face here. We will also go ahead and make sure that these two plates are coincident. No, I don't want to do that. There we go. So grab that and pull it down there. And then we'll just make that flush with that. Okay, cool. So now that we've got that, we're going to do what's called a whole component. It's in assembly whole series. It's in assembly features, and then you'll see that this tab comes up, and we're going to be using. Are we going to be using existing holes? I don't think we are. So we use that right there. We use that right there. And we use that right there. If you can't tell why I'm getting the middle to select, I'm selecting the outside, and then that little plus you can see just to the left right there, the little plus shows up, and then I can select that. And so we're not going to hit check. We're going to go over here. We're going to specify what kind of hole we want. We want this to be for a 10. We want this to be screw clearance. We could set something up to be like countersunk or something, but we don't need that because this whole plate right here is not countersunk. We might end up choosing that in the future, but we're not going to do that right now. Yep, close fit. Yep, sure. That's all good. Middle hole, end hole. Yeah, you don't need to mess with middle hole, end hole much unless you're doing something fancy. I think there might be a way to make some threading on here. Not sure. I think that's in Hole Wizard, I think. But we'll go ahead and we'll do that. What do you mean? I guess we're using existing holes. Am I doing this right? I don't think I'm doing this right. No, we're creating new holes. I don't know why it's going up there. Can you flip around? What are you doing? You can't tell, it's been a while since I've tried to use this. Okay, will you work now? What do you mean there's no bodies to cut? Maybe he's trying to go up. Why are you trying to go up? Maybe I selected the wrong thing. Okay. I probably selected it on the bottom and I thought I had to go up instead of go down. And I didn't see anything to flip on that, so I couldn't change that. So we'll be sure to select that. And we don't want to select the bottom one, we select the top one. And there we go, we can see it goes down. It actually does mess up with my hex just a little bit, so we'll have to change that later. But whenever we do that, yep, 10, everything's good. There we go. Okay, so the issue there was with my selection. It was just a little weird the way I had it selected to where it tried to go up instead of trying to go down. But if you can see, now it's made a hole through the part. And that is super useful in the future because I don't want to have to, if this is like a super complicated geometry, I don't want to have to replicate this and then paste it on this and then try to do all these different things. I can just use an assembly feature to do that. It's also a similar process for all these, except it'll apply that to the whole assembly rather than just the part. So it's like an assembly, it's literally an assembly feature rather than a part feature. So we'll go ahead and we'll use a fillet. So I want to fillet this whole thing. But I want to go 0.5 inches, and that should go down, and it's not. Why? Do I have to select you too? I don't know. I don't know why you could ever choose this instead of just doing a regular fillet. Oh, you can hear my dog. All right. It's Easter and my relatives have just come over. I swear I'm social distancing. It's just my sisters. So I'm gonna end this real fast. We're gonna go over mirror components. In linear component pattern, we're gonna mirror our components. And so to do so, we haven't properly set up. What we need to do is we need to go back and we need to set a reference geometry. And so we have the plane right here. We need to make a new plane. And so our first reference is going to be right here. That's good enough for me. It's going to be a 0 offset away. And I'd say that's pretty darn good. And then before we deselect that, we're going to mate. Wait, no, we're not going to mate. Oopsies. We're going to select that. And then we're going to go down to mirror components. And then it'll already select it as our mirror plane. And then we need to select our components. And a little note, whenever, oh, it's not actually showing up the difference. So I'll just go ahead and select all of those. Check, check, check. All right, and then there we go. It has mirrored. I'm sorry if that was a really, really short guide on mirroring, but I really gotta go. If you have any notes, let me know. I decided against doing a meeting at 3 because I figured I was probably not going to be available then anyway, and you guys probably aren't going to either. We should be available by 6. I hope we're all available by 6, but that's whenever the Zoom is going to start. So please be there. Just go ahead and watch this on your own time. And I'm really excited. I'll see you guys later. So let me show this. No, I don't want to see that. How do I show the thing? There we go. All right.